Okay, so this is the chapter 12 homework. So we start out, they give us the weight. They give us the weight and initial and final velocities, and then they give us a function for our force, our net force, as a force as a function of v. So I drew my little free body diagram, and let's just ignore these ones for a minute. So just this net force equals ma, and so I started solving it this way to get that function of a. So there's my function of a as a function of v, and if we remember from our equation sheet, if we remember from our equation sheet, a is a function of v, that's a equals dv dt, which we can rearrange to be dt equals dv over dA, which is the same as dt equals 1 over a times dv. So I went ahead and took this 1 over 0.0735 out of the integrand, and then I just had 1 over 3 v dv, and I integrated that. And so if I integrate on this side, I'm just left with t. So I integrated that and solved. And then I solved a dx v dv, which again comes from this equation here. Or no, sorry, it comes from this equation here. A as a acceleration as a function of position, because we need to solve for our x. I went ahead and divided both sides by a, and then solved because a is already a constant of v, or a function of v. So then I went through and solved. And then again, I took that same thing. I took that out of the integrand just to make it less messy. And then, yeah, that was that one. So this one was a little tricky for me. So this one we're given the mass, the length, or initial velocity, and we're told it is a constant speed. So I did my free body diagram and took my sum of the forces in the y direction as 0. It's not accelerating in the y direction. So then I set t cosine of theta, and it's cosine because we're talking about this theta. So t cosine of theta equals mg. T cosine of theta equals mg. And then I went over here to sum of my forces in the x direction, and I said that, oops, we're missing one right there. T sine theta equals MA, so like F equals MA in the x direction. And we said that A is the same as V squared over R. So I just went ahead and subbed in my R and then solved for T. So that's this equation here. Oh, and then based on the picture, this is L sine theta, because that's theta, and this is L. So if I call that R, then I can sub this equation into here, and then solve for, and then plug this equation that we solved for t into this equation, mg cosine theta, and then I went ahead and multiplied both sides by cosine and both sides by sine, and so then I have mg sine squared times theta cosine. And then I canceled out m's on both sides, and then I turned sine squared theta into 1 minus cosine squared. And then I turned this equation into a quadratic. So I went over here and pretended that it were just that x equals cosine theta, and then solved for x, and then plugged that back in as cosine theta, and then did inverse cosine to get my theta. Then after that, it's just a matter of solving my theta in for t. Wait, I actually wanted that boxed. Well, that arrow is fine. We'll leave that arrow. That's an arrow. A 500-pound truck. Yeah. So this one, again, I drew my free body diagram. And I'm pretty sure the solutions manual is wrong. So I just ignored the solutions manual. So sum of the forces in the x direction equals ma. And so that's force. So that's positive force minus tension equals ma, and for m we just use weight divided by g equals m, and then we just solved, then we isolated our f. Now over here we have tension going up and weight of both a and b going down, and so the sum of the forces in the y direction equals ma, and we know that this is this acceleration is the same as this acceleration, so we know that that's still that 1 feet per second. So we go ahead and subtract that over to get t, and those are all constants, so I got my constant, and then I take this and plug it in here to get my f. And then that actually is the tethered ball problem that I solved over here, so I'm just going to skip it. I accidentally pasted it twice. I know, silly. So this one, kind of the key here was recognizing that at max swing, velocity equals 0. So we have the weight of the ball going down and the tension, and we have the force of tension going up at an angle. And since this is 20 degrees, I said this was 70 degrees. I know that really doesn't matter, but I just like to have my sines be y and my cosines be x. So anyway. So since those are the only two forces at this point, I can go ahead and solve for t. I can go ahead and solve for t. And this one was a little bit trickier, but a sub centripetal acceleration is equal to velocity squared over r. So I subbed that in, and we have velocity and r. So I just went ahead and isolated for tension, and that is what I got. This is the turntable problem. They gave us acceleration in the tangential direction, and we can use this equation here to solve for v final. So we can then use this as our v final equals 2.4 meters per second. So for the orbital one, we have this main equation, and we have to keep in mind that, again, centripetal acceleration is v squared over r. So we plug in our f as this, and our a right here, and we're going to go ahead and cancel off our m's, and then multiply by r on both sides. And once we're here, we're going to multiply by r. And now we have gm equals vr, which we can calculate. And now that gm divided, which we have that calculation here as our gm, we can divide that by the gravitational constant given here. That's also in the back of the book. And then that will give us our mass of the sun. And then if we take that same equation, F equals ma, but instead it's mg, and we're solving for g, we can cancel off those m's again and then just solve for g that way. This one was very confusing, and I think the picture was drawn wrong, but we said u equals I over r, and we took this equation that you gave us here of 2 over rho naught equals f over mh squared u2, and then we said if u equals IR, then we can sub this u right here for 1 over r squared, and then that'll give us this equation, which proves that f is inversely proportional to the square of r. Okay, on this one, first I subbed in, again, this is my f. So this is my f right here. So I did f equals mg, and so that means g big M over r squared equals g, because we can just go ahead and cancel those m's again. And I multiplied the r over to this other side. And so I have this one and this one, which means I can, so f equals ma. For f, we're going to plug that equation in again. And for a, we're going to plug in our v squared over r again and cancel off our m's and our r. And then we're going to square root the whole thing. And that will give us our velocity, our centripetal velocity. And then you just multiply that by square root of 2, and that should give you your escaping velocity. This one was the hardest question. For our ellipse, we're given these main equations from the book. I couldn't find them in your slides, but in the book, I was able to find this one. So we can go ahead and set equal to that, and remember that cosine of b is defined here and cosine of a is defined there, which means cosine of b plus a is always going to be 180. And because of that, instead of writing how we did up here, where equals this, RA equals plus cosine of a and plus cosine of b, if we realize that a is just the negative of b, we can just have cosine here and negative cosine here. And really that's the trick. That's the key to the whole problem. Because if you can do that, then when you add these two equations together, you can cancel these out, and then you'll just get 1 plus RA equals 2 GM over h squared, which then dividing by 2, that gives you the half. And that's half of the equation you gave us. Now the other half So we're trying to get it to equal this, right? The other half is just substituting equations. So we have v equals h over r, and we have a equals v squared over rho. So if we sub this into here, if we sub this in for my v, then we have a equals h squared over r squared rho. So then when we have f equals ma, for a, let's sub this in here. And for f, let's use that gravitational force equation. And then cancel off our m's, cancel off our squareds, and we have gm equals h squared over rho. And then if we just divide both sides by h squared, boom, that's the exact equation that we had, we have up here. And so if we just bring them both down, we've proved it. Okay, thank you.